Hey there, thanks for opening up your science sketchbook. Today, I'm going to be giving you some must-know background information on radical halogenation, so that you'll know what's happening in the mechanisms. This topic can be super detailed, but I'm just going to give you the essentials. So, to kind of orient you to the main idea here, this is the general reaction setup for a radical halogenation. X is a halogen like chlorine or bromine, and you've got some light or radiation or heat to kickstart the reaction. The end product just basically puts a halogen on a molecule, even one with no other landmarks like leaving groups or pi bonds. This is accomplished through a radical reaction. So, meet the radical. It is basically just a single electron, like a little ball that's going to be tossed around in these reactions. Oops, got Sketch's attention there. Well, let's see how to toss this thing. To get it moving and attacking in a mechanism, you'll be using a half-hooked arrow. This emphasizes that you are moving just one single electron, not a pair like usual. So wow, look at it go. So, we know what a radical is, but what are some key features? Well, simply put, they have some similarities to carbocations. They have the same molecular geometry, trigonal planar, because they are also sp2 hybridized. They also have the same stability trends, where placing it on a more substituted carbon is more stable. Again, just like carbocations. Now, they can even rearrange, but they do it in a way that's quite different from carbocations, so I won't be covering that in this video. So, let's look at what these two features mean for radical reactions. Well, with that same geometry of trigonal planar, that means when a halogen radical comes to bond with the substrate, it can approach from both the front and the back side, since there's nothing sticking out in any particular direction. That means, if you bond to a chiral center, you'll be forming a racemic mixture of enantiomers. Basically half and half attack from the front or the back. So keep that in mind for your products. What about stability? Let me remind you of the general trend, which is the same for your carbocations once again. Basically, the less substituted the radical is, the less stable. So, for example, a primary radical is less stable than a secondary, and that's less stable than a tertiary. There are ones that are even worse too, like a methyl radical or a vinyl radical. But above all of these is the allylic position. That's just a carbon one away from a double bond, regardless of number of other carbons around it. As we get into the reactions, we'll talk about specific reagents that particularly select for this to occur, by the way. So, look at this example. Just like our template of the reaction, you will basically just be adding a halogen to the substrate. But how do you know where? Just think of where the radical intermediate would have been the most stable. So between these two, which one do you think would be the major product? Yep, it is the tertiary product as your major, because a tertiary radical is more stable than the secondary option. So now that we know all about what a radical is, let's talk about how it can form. Again, recall these reactions include halogens bonded to each other, and they need to separate to initiate the reaction. So you know how one bond line equals 2 electrons? Well, you will be splitting them apart homolytically. This just means one electron goes to one side and the other electron goes to the other. Both atoms get an equal single electron to become a radical. To make this happen, we need something to catalyze the reaction to make them split apart. You can do this photochemically using light, also denoted as HV for the constant and wavelength frequency. So just imagine that it zaps that bond in half. And that will form 2 bromine radicals. Let's rewind again to try with a different catalyst, heat. So, just like before, imagine you are heating it so much that it burns it in half, right? It splits it in half. So again, still forming the 2 radicals. So either the light, radiation, or heat, or both might be present for these reactions. So we just covered what a radical is and how to form it. Now let's talk about which atoms exactly are involved in a radical halogenation. For these reactions, you will focus on using bromine and chlorine. You won't be focusing on fluorine or iodine here because fluorine is a bit too reactive and iodine is too unreactive. So neither are exactly practical to bother with. So then let's focus in on bromine and chlorine. What's the difference between using these in a radical reaction? Well, to start, bromine is less reactive than chlorine. So much so that the first step of the propagation phase, where the halogen forms a radical on the substrate, is endothermic. For chlorine, it's more reactive, and this first step during propagation is exothermic. If you take a look at the energy diagram for this step in radical bromination, It needs to actually take in a lot of energy to have that bromine steal a hydrogen from the substrate and form that radical. Compare that with the energy diagram for chlorine, which actually releases energy in the process. This feature explains their next difference. Well, bromine is actually more picky about where it adds onto because of that big energy hurdle. For these reactions, just think bromine, your bro, gets the most stable seat on your substrate for its major product. Chlorine, being very reactive, is not picky at all. You can't quite predict the major product too well because it will literally end up anywhere. So your chlorine is too cool to care, it'll just add right onto most carbons indiscriminately. Let's see an example. Say you react propane with bromine and light. You'll form these two products. But experimentally, you'll find that 97% of the products formed will be the secondary bromine, as opposed to the mere 3% of the primary bromine. The same reaction, but with chlorine, will also form the two similar products, but look, only 55% of the products formed were the secondary, more stable position. That's almost equal to the amount of primary chlorine formed. So it's not exactly very ideal if you have a specific product in mind. Well, with that, that's all the context I think you'll need for this concept. To summarize, here is a reminder of the typical reaction you'll carry out. And remember, first, radicals mimic carbocation geometry and stability. This will impact how the halogens add on and in what spatial orientation. Next, remember that you can form halogen radicals under light or heat conditions. It'll split the bond in half homolytically. And finally, we typically use bromine and chlorine for these reactions. But remember, bromine is the one that is selective for the most stable carbon radical position. Alright, got all that? If you want to learn more, check out the mechanisms on my channel and subscribe so you don't miss any organic chemistry tips and tricks. That's all for now then, and I will see you later. Bye!